Greetings, everyone. This is Professor Jeff Wilkerson at Luther College bringing you an introduction to Exercise 22, Spectral Classification from Astronomers as Observers and Experimenters, published by Kendall Hunt. What I like about this exercise, so this is just going to be a brief introduction. There are a number of things I like about this exercise. One of the things I like about the exercise is the historical importance of the activity. The idea of spectral classification as a tool for measuring stellar temperature. And then using that, it's a quick and easy way to get the temperature of a lot of stars. So you see a picture like this where you can get a spectrum of a lot of different stars and an objective prism spectrum of a lot of different stars at one time. This was a very powerful way to get the temperatures of a lot of stars at one time. If we knew the parallax distances, then we can know that luminosities, and it leads us directly to being able to make HR diagrams and understand stellar structure and stellar evolution. And it's just one of the early steps in the path toward this understanding. And so this was Annie Cannon developed a really powerful tool here in order to help us understand a lot about stellar structure and evolution and stars. And so this is that historical importance. That's one thing that really drives my interest in an exercise like this. Another thing that's interesting is a lot of these exercises, a lot of the activities that we have in this textbook, they sort of couple very simple with quite complex. And that's what you have going on here. The idea is simple, and it's a relatively simple activity to complete, and yet it's a pretty tricky activity to complete. So that you see the sample spectra here, you see that you can look at the activity the book walks you through using these, and then coming over here and identifying these stars and saying which of these stars does this most look like, and is it between which stars, and making an estimation of the spectral classification. The spectral classification going O, B, A, F, G, K, M, 0 to 9 in each subclassification, in each classification. So you're looking to see if you can identify, for example, the sun as a G2 star. We should be able to look at the spectrum of the sun based on the strengths of the absorption lines and those strengths of those absorptions. So there's another thing I like about this. It's a reminder to us that the strengths of those absorption lines are really not dependent in any significant way on the chemical composition. Not exactly true, but in a large part, they're much more dependent on the temperatures of the stars, the temperatures of the photospheres of the stars, than they are on the chemical composition of the stars. All of these stars have a significant amount of hydrogen in them, but not all of these stars have a significant hydrogen lines visible, and that's because they don't have the levels populated. The n=2 level isn't populated in a significant way for a lot of these stars because they're simply too cool to have electrons up in that second level of hydrogen. So this is a reminder to us of some of the structure of what's going on there, to tell us that the spectrum, our first inclination would be to think that the lines in the spectrum are most importantly telling us what chemical elements are there, and they do tell us what chemical elements are there, and particularly for the later stars that might be somewhat useful, but it's not that's not the main driver of these lines, and they're really telling us about the temperatures of the stars is what they're doing. The other thing, we get back to this idea of simple and complex. The combination. So it's relatively straightforward idea to say, let's see what lines are prominent. Let's see what lines are prominent in our stars, and let's make that map across there. Once you start to do it, you realize it's not that simple a task. It's actually fairly challenging to make this work. And so you have to work pretty hard to identify these lines, and you recognize how technology might help you out. Doing this by eye is challenging. If you had a densitometer, if you were able to measure the brightness and the darkness across these spectra, as you would now, these were taken on photographic plates. Now with digital cameras, you would get this relatively quickly. You would be able to measure the brightness and the depth of these lines. You would be able to measure how dark the lines are relative to the continua around them. and be able to do this classification in a little bit more automated way. But you see how this was a challenge for early people working with these stellar spectra and trying to understand these stars. Likewise, the spectra, there's a similarity there, a resonance with measuring spectra, to say that if we were doing this with spectra instead of spectral classification, so if we were measuring these lines with a diffraction grating for a single star at a time is what I mean, and making a graph of something like this, there's so many lines in this is intensity and the function of wavelength. There's so many lines in a spectrum like that. Spectral identification is very challenging. And you don't know what the ionization states of the various atoms are. And it's just a lot of hard work by people who first started doing spectral analysis that way to try to understand what all lines were in the spectra of stars. And you get a hint of that here in this activity. And that leads us to one more thing. Oftentimes in the spectra of stars, there are lines that overlap that could come from the third ionized state of one element versus the second ionized state of another. And then you have to start looking for patterns, for pairs or sets of lines that move, that are always there together, that tell you about what the elements are right there. And likewise here, there's a warning to you in the text that at least one of these stars is two superposed stars. So you have either a binary star or at least a visual alignment of two stars that are right there, and the spectra overlap. And then it gets confusing because you get dark lines from stars that might be of two very different spectral classes, and they fill in there. And that's always the case. So there's always issues. Everything's always more complicated than it seems. The other thing that's a reminder here is the observational bias that we like to talk about a lot, is that we get the stars of these different spectral classifications, and we have to remember that the brighter stars are easier to see. The stars that are over here, we can see a lot further into space because they're brighter, they're more luminous. The stars that are down in here are very difficult to see. They have to be pretty near us. And so we might overestimate the number of these stars relative to these stars as we do an exercise like this. So this is a great exercise to remind us of things like observational bias, to help us understand the historical importance of measuring spectral classification and classifying stars this way, and then finally to remind us that this is a challenge. This work is simple on the surface, as a lot of work is, but if you really want to do it at the level you need to do it to get it right, it takes a lot of care and a lot of careful work and understanding of what's going on in there. So that's really what we have for the introduction. Is you jump in there and you've got something like 30 stars on this sheet. I think it's 30 stars exactly, with the spectra labeled here. In near Gamma Cygni, I think, is where this image is taken. So in Cygnus the Swan. And so of those 30 stars, see how easy it is. How many of those stars do you think you can do a pretty good job of analyzing the spectra and doing a spectral classification of? And how many stars do you think you can do an okay job, and how many stars are just really challenging? How difficult is it to measure the spectra of some of these stars? So good luck with it. As always, let me know if you have any questions, and I hope you find it interesting.